Oh, welcome back. So today this video is going to talk about the history of the atom. And we're not going to get too much into it, but this will be about as much history as you will get in this class. So first of all, you're familiar with what an atom is, right? An atom is just defined as the smallest particle of an element that retains the properties of the element. And as we mentioned in class before, atoms are small. You know, the world population is probably approaching 8 billion if it hasn't surpassed that already, which, if you're a fan of scientific notation, that is pretty close to roughly 8 times 10 to the 9th people. So there's a lot of people on the planet. But if we compare that to, for example, how many atoms are in a single penny, and again, estimate it's maybe probably like 2.1 times 10 to the 22nd atoms. Right? If you look at these powers of 10, notice that there's, a lot more atoms in a penny than there are people on this planet. So that just tells you how small a penny or an atom is. So the first person that is given any credit for contributing anything to atomic theory or the atom was a Greek philosopher called Democritus. And he was lived well over 2,000 years old. And he was not a scientist, he was a philosopher. And what he proposed was that matter was composed of something, a material or whatever called atomos, which moved through empty space. Now, I mentioned just a second ago that Democritus was not a scientist. He proposed a thought experiment where if you take something like it's any object, whether that be a piece of paper or something, and if you cut it in half and then cut it in half and cut it in half again and cut it in half again, and if you keep on cutting something in half, you'll get to a point that you would no longer be able to divide it. And that's what he called this atomos. Said that these atoms basically are solid, homogeneous, indestructible, and indivisible. Again, had no scientific evidence to back up his ideas because he was a philosopher and this was a thought experiment. But you can see just on that thought experiment was pretty effective because, yes, that logic would hold true for the most part. Another thing to keep in mind, remember, is that 2,000 years ago, we're talking about BC times. If you want to think about what they considered chemistry or what their periodic table would look like, right? It would look nothing like ours. It would basically, they were under the assumption that everything was made up of either one of the 4 elements, right? Fire, air, wind, and earth. They were the original airbenders, and everything changed when the Fire Nation attacked. So that's what they're working with, and that's a pretty good contribution with his thought experiment here. And you can see over the years, right, we still call the smallest part of an atom, and so you can see even through history, this type of terminology kind of stuck. So that's kind of a good importance. Now, if we fast forward to close to the beginning of the 19th century, so John Dalton, an American, was credited with developing scientific theory. And his theory was naturally called the Dalton's atomic theory. And he said that matter is composed of extremely small particles called atoms, so that part of Democritus stuck. And that atoms are indivisible and indestructible. So that part also kind of stuck. And also, you want to be thinking about what type of technology was present in this time in our history on the planet. Think about like what modes of transport were available in 1800. What had just transpired. It's like, people were rolling around in horses and carriages, and the American Revolution had just finished not too long ago, right? So if you're thinking about, from a technology standpoint, that helps frame a lot of these contributions because they were pretty groundbreaking for their time. So atoms of a given element, according to Dalton, are different in mass and size and chemical properties. Okay, so basically said that atoms of an element had the same mass, had the same size. And that's pretty good. Atoms of different elements obviously were different in that way. Also said that atoms of a specific element, as we just kind of mentioned, are different than other elements, where Democritus did not make any distinction between those. They said that all atoms were solid, homogeneous, indestructible, and indivisible. Different atoms then can combine in simple whole number ratios to form compounds. Right? And if this is confusing to you, what is a simple whole number ratio? It just says that, right, carbon dioxide reacts in a 1 carbon to 2 oxygens. Right? You're not going to have CO 1.5. Right? You can't have a partial atom in a compound. Then in any chemical reaction, atoms are separated, combined, or rearranged. Now, as you're looking over this, you probably have been able to figure out what parts were incorrect and that had to change with the times. But keep in mind, scientific progress, just like engineering progress, is iterative in nature. In the sense that what iterative means, if you're unfamiliar, is that it means the people who come after, the scientists and engineers that come after previous scientists and engineers, kind of take with what they had and improve upon it, right? If you think about this, if you think that a car company introduces a new model of car, do they start at from scratch to build each new model year of the same car? It's like, no, they take what they had and then improve upon it or slightly change things. And that's kind of how scientific progress is. Like, this is a pretty good achievement by Dalton, which this would have probably piggybacked upon some scientists before him that we're not talking about. But you can probably see two parts of Dalton's atomic theory were correct. One is that atoms of the same element are not identical. And the second thing is atoms are also divisible. Right? We can split an atom into subatomic particles. And that was not something that was capable or to be done back in the early 1800s. All right. So next step on our travel through history is roughly 1897, and this is going to be a British scientist, J.J. Thomson, and he was performing experiments with a cathode ray tube, and he was given credit that the atom was made up of even smaller particles. Okay, and what he saw was that as he passed current through the gas in a cathode ray tube, and on page 2 there's a diagram of a cathode ray tube, so you can kind of see that. He passed an electric current through the gas, and it gave off negatively charged particles. And since he knew the gas atoms in the cathode ray tube, it was sealed off, he knew they were neutral. That means that these negative charges, negative particles, had to come from the atom. And so basically was given credit for discovering what we know now as the electron. But he initially called them corpuscles, which one, that's not a very appealing sounding word, and it was changed at some point to electrons. Okay, so we look at our cathode ray tube this way. So again, it's sealed off with gas, and there's like a charged plates on both sides to help deflect anything that has a charge, either positive or negative, and pass current through it, and basically create a beam of electrons, negatively charged particles, which were detected at this end. So he was able to say that there is some particle that composed the atom that was negative in nature, but he could never actually find the particle. He didn't have the technology to do so. And he proposed a model of the atom that is sometimes referred to as the plum pudding model because he's British. Plum pudding is a British dessert. And what that said, and I'll give you an American analog possibly, is that a atom was a spherically shaped atom composed of uniformly distributed positive charge, in which individually negatively charged particles, or what we know as electrons, resided. Now, I'm sure most of you have no idea what plum pudding is. You may have heard about it in, some, maybe, I don't know if they reference it in Willy Wonka's Chocolate Factory or in A Christmas Story or but it's a British dessert. I would, for the American audience, instead of plum pudding, I would just call it like the chocolate chip cookie model. Because, right, he said that atoms are spherical in nature, and they had these negatively charged particles inside the atom, which was uniformly positively charged. So it's like in the cookie, chocolate chip cookie model, if you want to call it that, the negative charges, the electrons and the corpuscles, would represent the chocolate chips. And then everything that wasn't a chocolate chip would be the positively charged matter. Okay, so that's what what J.J. Thomson came up with his cathode ray tube experiment and the plum pudding model. And then not so long afterwards, right, Thomson was 1897, Rutherford here was 1911, and his experiment was a gold foil experiment where he took a thin sheet of gold and he had a source of alpha particles. And we're not going to get into radiation and nuclear chemistry this year, but alpha particles are essentially a helium nucleus. So let's say an alpha particle is basically a helium nucleus. And so they're positively charged. And so his gold foil was positively charged particles. So firing a stream of tiny positively charged particles, referred to as alpha particles, at a thin sheet of gold foil. And what he found was that most of the particles pass right through the gold atoms in the sheet without changing course at all. But a small amount of these positively charged particles did deflect away as if they'd hit something solid. And since he knew that positive charges repel positive charges, he was able to determine that the gold atoms in the sheet were mostly empty space. Right, and that's a pretty big discovery. Right, because it would be, the common knowledge up until that point was, from what J.J. Thomson was saying, is that, the atom was mostly positive charge, just with some negatively charged electrons kind of mixed in. That'd be like if you were to take a running start at a wall in your room. You'd expect if this is you running towards the wall in your room, to hit the wall and be kind of repelled backwards. Or if you really got a good thing in and you're at a pretty, just drywall and no reinforcement, maybe you can break right through, but like you're the Kool-Aid man. But what he was seeing is that most of them passed through without any issues, and then some of them even deflected in various ways. But he really wasn't seeing a whole lot of thing, being reflected back towards that. So he was able to conclusively say that the atom is mainly empty space. Okay, so he theorized that the atom had a small, dense, positively charged center, which he referred to or called the nucleus, and that the nucleus is tiny or small compared to the atom as a whole. And so all of the atoms positively charged particles were contained in the nucleus, and the negatively charged particles were scattered outside the nucleus. Okay. Again, at this point, the only subatomic particle that had been discovered was the electron, and Rutherford was just saying that, wait a minute, there's got to be some more matter or subatomic particles in the atom, but they're all going to be gathered in the center, and it's going to have an overall positive charge. Okay. Was not credited with discovering the proton or the neutron. That would come later with Moseley and some other scientists in the early 20th century. So, just a review, particles that compose the atom. Okay. 3 particles that you're aware of from 8th grade science or other science courses before there. Proton, neutron, electron. Right. The symbol for all of these are, or you can say P 1/1 P, or P with a positive sign. Neutron, electron is a 0/-1 E, or just E minus, and a neutron is either NO or 1/0 N. Now, what this represents here, the 1/1 or the 0/-1 or the 1/1, that is going to be an isotope notation, which I'm going to get into. And keep in mind that these letters, the P and the E and the N, all those are lowercase, okay, which differentiates them from an elemental symbol, because those are going to start with with a capital letter. These 3 things, since they're subatomic particles, they get a lowercase letter to start them. But the relative charge, proton has a relative charge of +1, the electron -1, neutron is 0, or sometimes I will abbreviate, right, NC, no charge. The relative mass, 1 and 1, and the electron is pretty much 1/10,000th of a mass. And the mass you hear about is the AMU, the atomic mass unit is what it's short for, and we'll talk about that later. And the location of these particles, right, that's in the nucleus, the neutron's in the nucleus, and this is in the appropriately named electron cloud. Okay, and just as a general overview of like a pictorial depiction of these models, Democritus, right, he just said that all atoms are tiny, indivisible, and indestructible. He didn't really say anything about shape, size, whatever. Dalton came along and he said that they're all homogeneous, for the same atoms of the same element are homogeneous. So they would all be the same size and have the same mass. Thomson said he was starting to look at that, the our plum pudding or the chocolate chip cookie model, kind of like it was spherical in shape, but you had everything was positively charged, and you had these pockets of negatively charged particles within them. And then Rutherford was saying, okay, there's a nucleus where all the positive charges are, and then these electrons were free to kind of orbit or around the surface or whatever in a 3-dimensional space. Okay? We'll see you in the next video.